Today we're going to look at electrolysis, okay, and we're going to be looking at different types of electrolytic cells, okay. Now, an electrolytic cell, unlike a voltaic cell is a cell that generates electricity, okay. An electrolytic cell consumes electricity, And the first type of electrolytic cell, or the first application of electrolysis that we're going to look at, is the electrolysis of ionic compounds, okay. More specifically, the electrolysis of molten ionic compounds. So let's say, for example, I want to electrolyze molten sodium chloride. Okay, so here, right, I want to electrolyze molten sodium chloride, right. So I have my container, right, in which I have molten sodium chloride. That would be NaCl liquid, right. So here I have NaCl liquid. Now, of course, in order to electrolyze or break down this ionic compound, right, again, lysis means the breakdown of, right, something. So hydrolysis is when we break something using, or we break bonds using water, right. Electrolysis is basically the breaking up of this ionic compound with the use of electricity, okay, with the use of electricity. So obviously, if we're going to consume electricity, we need electricity, right, and for that, we're going to have a power source, right. We're going to have a power source, right, and then we have these two electrodes, okay, and then we have our molten electrolyte, right. So the electrolyte here is molten sodium chloride. We have our electrodes, we have our power source, right. We have the positive terminal and the negative terminal. So again, when we talk about the electrolysis of molten ionic compounds, okay, it refers to the breakdown of ionic compounds into its constituent elements. Okay, the sodium will be broken down into sodium chloride will be broken down into sodium metal and chlorine gas, right. So when we talk about electrolysis, okay, the cations, okay, for ionic compounds, right, cations discharge at the cathode, okay, and anions discharge at the anode. Right, and again, we know that reduction takes place at the cathode and oxidation takes place at the anode, right. So the cations undergo reduction to form the metal, and the anion undergoes oxidation, right, loses electrons to form the non-metal. So over here we can say that the electrons are flowing, right, electrons flow from the negative terminal to the positive terminal, right. So here we can say that the electrons are going towards this electrode, right. So this is the cathode, right. This is where electrons will be gained, right. This is where reduction will take place. So we're going to call this the cathode, right, and then, okay, this is obviously going to be the anode, right. Again, the negatively charged terminal, or the negatively charged electrode, right. These electrodes are again going to be inert, so we're going to use, for example, a very common material that we use is graphite, right. Graphite is a very common material for these inert electrodes, right. They're unreactive but conductive, right. And the half equation that we have for the cathode here, right, the half equation that we have for the cathode is, right, again, it's negatively charged, right, it's negatively charged, so we have sodium gaining electrons to form sodium metal, right. So reduction is taking place at the cathode, right. So cations undergo reduction to form the metal, right, in this case, and then at the anode, oxidation would take place. So chloride ions will undergo oxidation, right. The anion will undergo oxidation. It will lose electrons to form chlorine. Right? So this is the half equation that we have for the anode. So of course, if we look at the overall equation for the electrolysis of molten sodium chloride, look at the overall equation, right? What do we get? we have NaCl, right, forming Na and Cl2, right? And you have, if you just balance the electrons here, right, you have 2 NaCl giving you 2 Na plus Cl2, right, if you balance the electrons here. This is the electrolysis of molten ionic compounds. Okay? The electrolysis of molten ionic compounds. Okay? Ionic compounds can be broken down into their constituent elements, right? And we're going to use a power source. So this is what we call an electrolytic cell. So we can say that the product at the cathode is sodium metal, and the product at the anode is chlorine gas. Okay, the product at the cathode is sodium metal, and the product at the anode is chlorine gas. So now let's say that instead of molten sodium chloride, I have something like molten silver oxide. Right, let's say I have liquid silver oxide. Right, so let's say that I have molten silver oxide, and the question is, what would be my products? Right, what would be my product at the anode, and what would be my product at the cathode? And I want you to write half equations for each of those electrodes as well. So again, at the cathode, right, electrons are flowing towards the cathode, right? That's where we're going to have reduction take place. So again, we're going to have reduction taking place at the cathode, right? So the silver ions, right, silver ions will gain electrons to form silver metal. So silver metal is our product at the cathode, right? And then remember, the anion will discharge at the anode, which is the positively charged terminal, right? So it will lose electrons, right? The anion will lose electrons at the anode, right? Remember, because oxidation takes place at the anode, right? So we know that the oxide ions, right? The oxide ion will undergo oxidation at the anode to form oxygen gas, right? So that will be our product at the anode. And then if we have 2O2 minus, right? Remember, each oxide ion loses 2 electrons. So if you have 2 oxide ions, we're going to have 4 electrons, right? Plus 4 electrons. Okay, so this is the half equation for the cathode, right? Reduction of silver ions to form silver metal. So the product of the cathode is silver metal, and then the product of the anode is oxygen gas. And for the overall electrolysis, right? For the overall electrolysis, our equation is Ag2O gives us Ag plus O2, right? And if you had to balance this, right? Looking at the half equations, right? We need 4 electrons for the cathode, right? So if you just multiply everything by 4, right, we get this, right? We get 4 Ag, we get 2 Ag2O gives us 4 Ag plus O2, right? So this is the equation for the electrolysis of molten silver oxide. Okay, so now we're going to look at the electrolysis of aqueous ionic compounds. Okay, so we're going to look at the electrolysis of aqueous ionic compounds, right? So now when we have aqueous ionic compounds, right, electrolysis of aqueous ionic compounds, right? So for example, right, now instead of looking at molten sodium chloride, let's say that we have dilute aqueous solution of sodium chloride. Okay, so we have dilute NaCl aqueous, right? And again, of course, the same thing applies, right? Cations will discharge at the cathode, and anions will discharge at the anode. When we talk about aqueous solutions, okay, right, if you look at the cathode, we know that reduction takes place at the cathode, right? And we have 2 different cations that can discharge at the cathode. We have Na plus or H plus, right? And we're going to go to the data booklet, and we're going to look at the standard electrode potentials for the reduction of sodium and H plus ions. Okay, so from the data booklet, we have Na plus, right? The standard reduction potential or standard electrode potential for the reduction of Na plus is negative 2.71 volts, right? And then the reduction potential for the reduction of H plus, standard reduction potential, right, for H plus to form hydrogen gas is 0.00 volts. So at the cathode, right, at the cathode we have to decide whether sodium metal forms or hydrogen gas forms, right? And we can clearly see that the reduction of Na plus ions is highly unfavorable, right? The standard reduction potential is negative 2.71, whereas the reduction of H plus ions, the reduction potential is 0.00. That's a big difference. Okay, that's a very significant difference, and it's like the possibility of sodium discharging is next to none, right? It's highly unlikely. So what you're gonna have here is, right, this is Na plus is far less reactive. Okay, so the discharge of sodium metal is highly unfavorable, and what you're gonna have is your product at the cathode will be hydrogen gas. Now over here for the anode, okay, for the anode, we're going to use the half equation for the discharge of water, okay, or the discharge of oxygen gas from water. Okay, so instead of the anion, instead of hydroxide being discharged, okay, we're gonna have H2O or chloride ions, okay, discharging at the anode, right? So for the discharge of oxygen gas from water, from H2O, we have the following equation. Okay? For the discharge of oxygen gas from H2O, we have the following equation. We have H2O gives us 2H2O gives us 4H plus O2 plus 4 electrons. Okay, 4 electrons. All right, so this is the discharge of oxygen at the anode. Okay, this particular half equation has a potential value of negative 1.23 volts. Okay, negative 1.23 volts, right? Or we can have chloride ions, right, forming chlorine gas at the anode, right? So that would be Cl minus, making Cl2 plus 2 electrons, right? Or Cl2 plus 2 electrons, right? So then we have 2 Cl minus here, right? And this has a value of negative 1.36 volts. Okay, so at the anode we can clearly see that the discharge of oxygen gas, right, the production of oxygen gas is much more favorable to the production of chlorine gas, right? Is more favorable. This value is less negative and this is more negative, right? So the discharge of chlorine is less favorable. It's more negative, the value. Okay, so over here we can say that instead of chlorine gas, we're going to have oxygen gas. Okay, so our product at the anode is oxygen gas, and our product at the cathode is hydrogen gas. So what you should remember is that when we talk about the cathode, right, for aqueous solutions, okay, when we talk about the cathode, we have a competition between the metal cations and H plus ions. Okay, we have a competition between the metal ions and H plus ions, whereas at the anode we have a competition between H2O and the anions. Okay, for alkaline solutions, instead of H2O, we're going to have the discharge of, or we're going to have the oxidation of hydroxide ions. Okay, but for neutral solutions, it will be H2O at the anode. So now we're going to look at what happens when we have saturated sodium chloride instead of dilute aqueous sodium chloride. Okay, so we have a saturated solution or a highly concentrated solution of sodium chloride. Now we have the same half equations, right? We have the same half equations, right, for the anode as well as the cathode, right? And again, we have to decide whether we're going to have hydrogen gas forming at the cathode or sodium metal. And at the anode, we have to decide whether we're going to have oxygen gas or chlorine gas. Okay. Now, if you have a highly saturated solution of sodium chloride, you have a very saturated solution of sodium chloride. Okay. What happens is the following. All right. If you look at the equilibria, let's look at the anode first. Right. What we see is that for these values that we're looking at from the data booklet, right, these are for 1 mole per dm cube solutions of ions, right? Now, obviously, for a dilute solution, we can use these values directly for our comparison. But when we have a concentrated or a highly concentrated solution here, what we've done is we've significantly increased the concentration of sodium ions and chloride ions, right? Which means that this equilibrium, or this is shifting more towards the chlorine, right, and this is shifting more towards the sodium, right. They are shifting more towards the chlorine and this is shifting more towards the sodium. If you compare the discharge of sodium with hydrogen, we can clearly see that the discharge of hydrogen is highly favorable relative to sodium. It is highly unfavorable. It's such a large difference, 2.71 volts, that even if you have a very, very large concentration of sodium, it will not make up the difference. Okay, so even with a saturated solution, our product at the cathode will be hydrogen gas. Okay, because of the very large difference. On the other hand, if you look at the difference for the discharge of oxygen versus chlorine at the anode, right, the difference is pretty small. Yes, the discharge of oxygen was more favorable in the dilute solution, right, but in the concentrated solution, again, what you've done is you increase the concentration of chloride ions, right, favoring the formation of chlorine gas. So therefore, this value has become less negative. Okay, it has become less negative. Okay, now as a rule of thumb, if the difference is lesser than 0.2 volts, okay, if the difference is lesser than 0.2 volts, okay, we can say that difference can be overcome. That difference can be overcome by an increase in concentration. Okay, again, we know that the discharge of chloride or chlorine gas is less favorable in the dilute solution, but because we have a very high concentration of chloride ions and the difference is not that large, right? This is the difference between these two values is just 0.13 volts. Okay, there's only slightly more unfavorable in dilute solution, but in concentrated solution, right, this difference, because it's lesser than 0.2 volts, it will be overcome by the increase in concentration of chloride ions. Okay, so what we can say here is that the increase in the concentration of chloride ions, okay, makes the E naught, right, or the electrode potential, or the potential for this cell, right, more positive or less negative than negative 1.23 volts. Okay, making the formation of chlorine gas more favorable. Okay, making the formation of chlorine more favorable. Okay, so therefore we can say that in a saturated solution, instead of oxygen gas being discharged at the anode, our product at the anode will be chlorine gas.